I'd like to turn to what was considered an ancient scourge of TB, tuberculosis.
Right.
What are you doing, and what are your efforts doing to bring the fight against and treatment and diagnosis of TB with modern therapeutics?
Right.
And how does synthetic biology factor into this?
Right. Well, that's an excellent question. And tuberculosis is one of those diseases of enduring a global health impact that has really been neglected, likely because of a good dose of complacency that it's somebody else's problem, not the developed world problem. If the numbers be known to many people, they would be shocked. 1/3 of the world's population is infected latently with tuberculosis. That's over 2 billion people. They're not sick, but they have latent TB. Yet, there are about 8 million new cases a year and about 1.3 million deaths per year of tuberculosis. The goal of what we're trying to do at NIAID and what other organizations are trying to do, the Fight TB and Stop TB initiatives, is to bring the science of tuberculosis into the 21st century. It's almost as if we were stuck in the mid and early 20th century. We haven't had, except for one exception, a new drug for tuberculosis in over 40 years. Just this past year, we had the first drug that was specifically approved only for TB. We have a very ineffective tuberculosis vaccine. We need a good one that works. We have diagnostics that are antiquated, that are still the ones that were used 75, 100 years ago, looking in a microscope for the tuberculosis. We don't have enough drugs. We have drugs that require 6 months to a year of therapy in order to suppress it. We need to play serious catch-up ball by bringing the science of tuberculosis into the 21st century, and we're doing that by aggressively applying many of the modern techniques, for example, of the ability to rapidly sequence strains of TB and identify vulnerable parts of that mycobacteria that are vulnerable to drugs, parts that code for antigens that might be used for a vaccine, ways of not only diagnosing TB, but determining at the point of care virtually immediately whether you're dealing with a resistant tuberculosis or not. These are things that are getting a major, major push, and it's only been, I would say, over the last 10 years at the most, that we have really come to the realization that we have got to stop playing 19th, 20th century baseball here and get into the ball game of modern technology.
And synthetic biology is a little bit
well,
like
synthetic biology.
Is that just one way of doing it?
Well, that's just one way of doing it. What that is that you create a microbe according to your own design, and you can manipulate it and look at different spots in that. But that not necessarily integral to where we need to go with tuberculosis.
Well, I want to get on. I want to dig a little deeper too, because you raised a question, or you asserted a number which really kind of perplexed me. 2 billion people with latent TB.
Yes.
What triggers the latency, what takes it out of latency and activates it, and how do you know that?
Well, okay, so you've asked the question that we should know the answer to, but we don't know the answer to. So if you look at the large group of people, the 2 billion plus who are latently infected with TB, about 10% of them during their lifetime will convert into active TB. If you are HIV infected, and you have a compromised immune system, there's a 10% per year likelihood that you will develop. So if you're an otherwise healthy person, you're going to develop active TB 10% over a lifetime. We don't know what those mechanisms are. We do know that when you suppress the body's immune defense mechanisms, you greatly increase the likelihood of developing active TB if you have latent TB. But we don't know why that spontaneously occurs over the lifetime in 10% of people. So that's one of the things that you put your finger on, is that we don't even understand the fundamental pathogenesis of tuberculosis. We don't understand the systems biology of the immune system. Why doesn't the immune system completely eradicate tuberculosis? Why do you always have a little bit that's there and latent? What is the proper immune response to protect you against acquisition of tuberculosis? We don't even know what that is.
Okay. I wanted to transition to malaria, which remains a global health threat. And I know when the typhoon hit the Philippines, unfortunately, there was real concern about outbreaks in malaria. What are you doing to respond to the global threat of malaria? And what are some of the new initiatives or key pharmacologies that you're using?
Well, malaria approach towards control, elimination, and hopefully eradication. The latter is going to be very difficult.
Okay.
We've accomplished the second one in several places, including the United States, the developed world, and even in some developing nations. Control is easy to do, but it's elusive because we have control mechanisms. So when you look about what are you going to do about malaria, there's an implementation of existing tools. We know that bed nets work, indoor spraying works, prophylaxis and treatment of pregnant women works, good treatment of people who are in high risk works. The implementation of that requires political, social, and national will. So there are things that you can do that you could dramatically control and maybe even eliminate malaria without any new scientific discoveries. On the other hand, there is a deep need for scientific discoveries. For example, first and foremost is a vaccine. This is a killer of 680,000 people a year, most of whom are African babies, generally infants, certainly children less than 5 years old. And yet we don't have a vaccine that works in these individuals. Now, the reasons for that are complicated because malaria is a very complicated parasite with multiple phases in its life cycle. But the thing that is a major target of research effort is to develop a malaria vaccine. And there have been, over the last several years, some optimism there with regard to vaccines that have been developed that are not ready for prime time in the sense of being highly effective, but at least getting us in the right direction. The other issue is the issue of treatment with drugs to which the malaria doesn't develop resistance. You know, back in the old days, quinine was it. You had it. You quickly cured people with malaria. And then, as is the case where we were discussing before, is that microbes have this inherent capability of developing resistance by mutating and changing. So we have a very good drug, which when used in combination, an artemisinin derivative. We're concerned, and we're starting to see inklings of this at the Cambodian-Thai border, where it isn't that resistance has developed yet, but the time to get to elimination of the parasite in someone is becoming longer and longer, which is the first step towards developing full-blown resistance. So we need to develop a more robust pipeline of new drugs so that when resistance occurs, we can replace the old drugs with new drugs. And we need better vector control. I mean, the old issue of spraying DDT, did work, but there were a lot of issues associated with that. We need better vector control. So there are two major buckets that I look at it. One is implement what you have, bed nets, indoor spraying, etc., but make a scientific push for the things that we don't have. Better drugs, better insect control, and certainly a malaria vaccine.
Well, Dr. Fauci, I had you on about 2009, right around the time of the pandemic, the influenza pandemic. What's been happening? What significant progress has been made in that area?
Well, the significant progress is, one, in the production of vaccines, which I don't consider very much the end game, so that we don't have to rely on growing it in eggs. We now can grow it in cell lines, which is an improvement in production, but in my mind, not a game-changing improvement in concept. To me, what we need to do, and we have some example of that, there's been an approved vaccine this year, which is using recombinant DNA technology so that you present the body with just the important protein that you wanted to make an immune response against. But for me and my colleagues in the field, the real goal is to develop what we call a universal influenza vaccine. And a universal influenza vaccine means that although influenzas change a bit from season to season and change a lot when you have a pandemic, the immune system makes responses against that part of the influenza which generally changes. That's why you need to get revaccinated each year and need a really new vaccine when there's a pandemic. A universal flu vaccine induces a response against that component of the influenza virus that doesn't change at all or changes very little from season to season or even when you have a pandemic. And we are getting closer and closer to that goal. So the exciting thing in influenza research that might solve the problem not only of needing a new seasonal influenza vaccine every season, but might also protect us ahead of time against the potential for a pandemic, is to develop a truly effective influenza vaccine that you may need to give once or 2 or 3 times throughout the lifetime of an individual to protect them against all strains.
While I was preparing for our conversation, I came across a very compelling article you wrote. And I want to get into it a little bit. There's some compelling research questions relevant to global health and pandemic preparedness,
Right.
including whether highly pathogenic viruses such as H5N1 have the ability to mutate or reassort.
Right.
Will that happen? Do you see that happening? What's the prognosis there? And is there a genetic signature of such a virus that would be helpful in surveillance?
Well, you picked a concrete, real example.
Okay.
So what's smoldering right now in Southeast Asia is H5N1, and what's smoldering in China is H7N9.
Okay.
These are 2 viruses that are fundamentally viruses of birds that have jumped species, rarely, into a human, but that have not developed yet or might not ever develop the capability of efficiently going from human to human. And the reason why you don't see problems right now with H5N1 or H7N9 is that it reaches a dead end. It infects a human, and it doesn't have that human infect another human, infect another human, and then you have what we call sustained transmissibility. There's not sustained transmissibility. However, we do know from experience that there are certain types of mutations that are associated with an increased capability of enhanced transmissibility from person to person. And that's what's being followed and being studied. Now, it isn't as simple as some people might make it, where one mutation means all of a sudden it's going to be highly transmissible. It's likely a multigenic phenomenon that requires host adaptability that goes well beyond a mutation. So the answer to your question is it is certainly possible that these viruses will mutate and adapt themselves better to transmissibility in human. For that reason, we've made a vaccine against the H5N1, and we're making a vaccine against the H7N9 just in case. But you'll ask, is it likely to happen?
Yeah.
Historically, you'd have to say it's unlikely. But when I say that, people will say, how can you say it's unlikely? You never know. And the answer is you're right. Because if there's anything about influenza that you can predict, is its unpredictability. But historically, given the number of viruses, particularly bird viruses that are out there, pig viruses that are out there, that intermittently infect humans and never make the transition to sustained transmissibility among humans, you can say that the chances of that happening is probably low, but certainly not zero, and that's the reason why you've got to continually be prepared to address a pandemic.